promise is really cool. If you end up, oh, now I can see the difference. If you end up making some significant progress, you can also publish it. Promise is really like connects you with a good amount of other people. So, do you guys know about RSI? RSI. Yeah. So, turns out RSI and promise has like really close connections. So, yeah, maybe try applying to RSI also. Anyways, so today's talk would be on enumerating rationals using Calkin Wilf tree. So we, I'll give you the basic outline of what we are going to do. We'll discuss about countability, uncountability, and we'll go and prove some basic results involved in it. We'll show rationals are countable. And I'll give you another proof of how rationals are countable using the Calkin Wilf tree. Introduction. Um, so do you guys know what countable is? When do we say a set is countable? So we say a set X is countable if there's a bijection between the set X and a subset of N. Okay. And we say two sets are of the same cardinality, whether infinite or finite, if I can make a bijection from A to B or B to A. And yeah, do you think N is countable or not countable? Countable. Just take the natural mapping. The phi of N goes to N. That's your bijection. Okay. Do you think Z is countable? The set of integers. Why? Yeah. Okay. So that works. What we'll do is, um, essentially what I'm going to do is 0, and then I'll just start from here and then go here and then go here. That is my first mapping. The second mapping is, well, the sigma n is, so sigma n is 1 if n is 0. Sigma n is 2 to the power n when mod of, like, when n is positive, and 3 to the power minus n when n is negative. Essentially what I'm doing is, I'm creating a mapping which is injective to n, and then I'll show that if I have an injection that is sufficient to show that the set is countable. Why? If an injection exists, then I can essentially create a bijection. So I can create a bijection, and that set B would be a subset of n, and that set B would essentially be have cardinality sort of less than n. So I can say that it is countable. Do you guys see why? Okay, nice. I'm going sort of quickly over it because I think most of the people are comfortable with it. Okay, okay. Okay. Yes. So now, my first question would be, is n cross n countable? Is z cross z countable? So forget about that. If I have a countable set A, is A cross A countable? So think about it. It is. So I need a mapping. Can you guys give me a mapping? Go on, say. That is true, but what's the Cantus proof? Huh, yes. Yep. I'm gonna use that for showing rationals are countable. So how about you show me rationals are countable after I am done with showing this? The same way, like you just go zigzag thingy. Yes, okay. I see. Anyway, so here I'm just going to create an injection mapping. And by the theorem I stated before, this would be self-sufficient. Okay. So what I'm going to do is if I have A comma B, I'll just map this to 2 to the power A, comma 3 to the power B. Oh, sorry, into 3 to the power B. And this is an injective function. Can you guys see how? Yep. Okay, nice. Let's just show it. If I have x1 comma y1 going to 2 to the power x1 comma 3 to the power y1, and then x2 comma y2 going to, then, and if these two are same, then by uniqueness of prime factorization, we are working over z, so it's unique. So uniqueness of prime factorization, we know that x1 is equal to x2 and y1 is equal to y2. Cool? Cool. Then I can generalize this method. See, this method worked because we are working with primes. And I know primes are infinite. So I can essentially go and show that a to the power n, where n is finite, is also countable. Great. Also, why restrict yourself to just A, just one set? You can just show A cross B is also countable, where A and B are countable. Great. Okay. So now that you guys are getting comfortable with countability stuffs, I can also have, well, unions of countable set to be countable. Can you guys see why? Yes? Hmm. And that should work. I think my idea, it was, I won't say it's my idea. I actually learned this idea in our real analysis course. So this is my professor's idea. I'll credit him. Um, Essentially, what you do is I'll pick whenever the first element, like so I want to map X, right? Since I know it's countable sets, I can number the sets A1 to up to AN, and then I can just uh, and since I know it's countable, I can have a mapping Fn from AN to the natural numbers. Now I want I'll take X, which is in the union, and what I'll do is I'll consider the first index I such that X belongs to AI. I have the notion of first because it's countable and uh yeah, it's countable. Okay. So then I can simply take fx to be 2 to the power I into 3 to the power fix. And this is an injective function going to the natural numbers. So it is countable. Do you guys see why it's injective? Yes? Take it. Good. I can do the same thing to show that rationals are countable. Hannah, essentially what I'll do is, essentially what I can do is if I have any m comma n, I can simply map it to, oh, this is positive. Also, I'm showing positive rationals are countable, and then it will, and then I have a zero to handle, and then I have negative rationals to handle. But if I show positive rationals are countable, then it's simple to show why the whole rationals are countable. So I'll just deal with m comma like positive rationals, and we'll figure out what the injection would be. So if I have m comma n, I'll just map it to 2 to the power m into 3 to the power n. Huh. There's one thing though. There's one sort of problem, small problem. when I'm dealing with rationals, I need the same rational number to map to same rational number. So what I'll do is to see. So if I have this mapping, give me two rational numbers. Let's say 4 comma 2, 6 comma 3. These two, when I deal with rational numbers, these two are the same rational numbers. So when I'm creating a mapping, they should map to the same thing, right? So just to not get confused and all, I'll just deal with m comma n such that the GCD is 1. Oh, this notation is fine, right? I don't write GCD here. I don't write that. I usually just do this, which is way better notation. Use that, please. Please. M comma n, no GCD. Cool. So I can show set of positive rational numbers are countable. Then I can show the whole set is countable. It's the same way I show Z is countable. Ooh. So you were suggesting this one? Yes. No, not really. Yes, yes, yes. Let's go. Were you there in Promise last time? Oh, okay. Were you there in ISC last time? No, okay. Oh, you were there. Okay, okay. Were you attending the special talks in ISC? Okay, so there was another guy like you. Okay, so how to show rationals are countable? This is one geometric way. You essentially write the the yes, correct. So when I know these two rational numbers are same, I'll just ignore it and move forward. Ignore. Uh, yeah, yeah. This was the mapping I was saying. So I know positive rational numbers. This thing was also for positive. So I know positive rational numbers are countable. I'll then consider this mapping, which is same as this thing, just more rigorously written. Uh-huh. Yes. Set of algebraic numbers. Okay. Do you guys know what algebraic number is? Okay, I'll define it for you guys. It's essentially these roots of rational polynomials. So if I have a polynomial an x to the power n, okay? Now these AIs, they belong to rationals. Oh. So the roots of this polynomial is called an algebraic number. So what I'm asking you is the set of algebraic numbers countable? Yes, yes. But there's another thing. This is algebraic number. There's something called algebraic integer, which is set of numbers which are roots of the polynomial x to the power n plus an minus 1 x to the power n minus 1 a naught, where an minus 1 belongs to the integer. Can you guys see why the polynomial has to be monic? Like, it has to be monic. I can't put a, yes, exactly. Else I can just take like the LCM of the terms and then multiply it with this and we can get it. Okay, so cool. Can you guys see why algebraic numbers are countable? Go ahead, tell you. Hmm. Mm-hmm. Yep. Yes. Yeah, correct. That is correct. So this is what's your name? Oh, Bhairav. Yeah. So what? Sorry. I think so too. We met in Bangalore, right? We'll figure it out when we met, but I know I have met you. I've heard this voice before. But yes, so we know algebraic numbers are countable. Why? As Bhairav suggested, we'll first fix the degree of the polynomial. And essentially that thing, the set of, and for each n degree polynomial, I have an n tuple, at most n tuple of roots. And then I'll just vary the n and I'll get the count. And since for each n, I get a countable set. I'll take the union. That is a countable set. Everybody is fine with it? You guys can go through the proof also if it's not clear. Stop me whenever you think I'm going too fast. I Is this, how many people know this thing before, sir? Oopsie. Like, you guys are, please ignore them. Oh, I guess I can introduce these people later also. These are my friends. Most of them at least. Anyway, so everybody is fine with this? Cool. These are uncountable. Very sad. So there are multiple proofs of why reals are uncountables. I guess many people know about the Cantor diagonalization proof. There's one which uses nested intervals. So I'll give you the nested interval wala proof, which is a bit technical. So bear with me if you guys don't know. Oh, I'll first define what a supremum of a set is. Sorry, sequence, not set, sequence. Supremum of a set is not defined. Do you guys know what a supremum of a no, set is also defined, right? Supremum of a set is also defined. Supremum of a sequence is also defined. Essentially, okay, firstly, we're going to talk about rationals. The set of rational is incomplete. As in, okay, I have this real nine. I have this real nine, and I can, so when we say a set is not complete, when I take a sequence and the sequence converges to some point, but that point is not inside the sequence. So here's an example. I'll just explain it, अच्छे से. You guys know what root 2 is, right? It's an irrational number. Now, what I'm telling you is consider all the rational numbers which sort of converges to root 2. So I have a sequence of rational numbers going very close to root 2, but it's not, but it, and it's like it's going towards root 2, but root 2 is not there in the set of rationals, which is bad. So essentially, I want, if a sequence converges, I want that the point it converges to be in the set. Then I can say it's sort of complete. When it doesn't converge to the point I want, like it doesn't converge, like the point it converges to is not there, I can say there are sort of holes. Okay? So yes. So reals are complete. Complete in the sense if I have a sequence, and then if it converges to that point, it converges to will also be there in that sequence in that set. So yes, supremum. Supremum is nothing. It's just okay. Anybody knows what supremum is? No, no, don't ask. Go on. No, he answered it. Can I not answer then? Okay. So yes. Yeah. Oh, yes. Go on. Say yes. Yes. The least upper bound, and that is the sup. Yes, correct. That everybody got what he said. Yes, supremum is the least upper bound. Supremum is something which is supremum is something which is bigger than the elements in the set, but it is the smallest biggest element, like smallest biggest bound. So least upper bound. Get it? That's cool. So yes, so that's what we need. And essentially, if I have a set which is like bounded above, so if I have a set, say X, which is bounded above, that is all the elements, is less than this number M, then I know its supremum exists. I'm taking that for granted. It's a thing which real numbers have. It's an axiom. Okay, guys, everyone, please pay attention. Thank you. So yes, that is enough to show why reals are uncountable. So this is going to be my construction. I'll say suppose not. Suppose it is countable. Then I should definitely have a bijective function. Forget about that. Yeah, actually a bijective function. From n to r. R is infinite. So there must be a bijective function from n itself, not a subset of n. N itself. Okay, this is fine. Now, essentially what I'll do is, how will I get the contradiction? I'll get the contradiction by saying that there is an element x. It's a bijective function. There is an element x in my construction such that x is not the pre-image of any number, any natural number. And then then it would be a contradiction. How will I get the number x? So my main idea is, I would like you guys to think about it. So that's why I'm not going to say the solution right now, like in the next 30 seconds. I'll give you guys some time to think. The hint is nested intervals. So think about it. If you haven't thought, I'll just tell what's happening here. Is key. I have a nested interval. I have an interval 0 to 1. Okay. If if f of 1 lies in this, then what you do is just consider a sub-interval of this such that f of 1 is not there in this interval. Is that clear how I'm doing it? So then uske baad I'll get an interval a comma b such that f of 1 is not there in this interval. Then if f of 2 is there in this interval, just simply take a sub-interval such that f of 2 is not there in that interval. I'll call that a1 b1. Similarly, a to b2, which is a sub-interval of this, and f2 does not, f3 does not belong to that interval. And you continue that process. What I'll get is, oh, you guys are there. Can you guys see this board? No, right? I'll erase that part. So what I'll do is, oh, sub-interval has this very interesting property कि if a comma b is a sub-interval of c comma d, then what do I have? I have c less than equal to a. Yep. So now remember my construction over there. I have 0 comma 1, a comma b, a1 comma b1, all are sub-intervals. So essentially I have a1, a2, a3, at, and then this is b1, b. Outside, like like the other endpoint. Yes. That's why we get this. Huh. Cool. This is fine. Now I know the supremum of this. The sequence is bounded by B. We are working in reals. So supremum of this sequence exists. I call that thing, give me a nice variable name, please. Uh, um, Alpha. Thank you. It's alpha. That's the supremum of the sequence. Do you think alpha will have a preimage? Preimage as in if there's any natural number such that f of n is equal to alpha. Do you think it should have a preimage? Huh, but then how's my construction going on? Yes, so I assumed the contrary. I assumed that there is. Then I said, okay, f of 1, f of 2. And now this is my construction, which is like I have I have 0 comma 1 initially. If f of 1 is there, then just consider a subinterval in which f of 1 is not there, which I can obviously do. Like if I have this interval, and I have this point, I want to remove this point from the interval, I can just consider this. More rigorously, just take half of it. So alpha is the supremum. So essentially, if for all n, alpha is just greater than equal to an. Hmm. So yes. Wait, okay, I'll let you guys read through this. That is our required. Did you guys follow why this is happening? Pakka? Should I explain more? Okay, nice. Yay! There's another proof. Do you guys know this one? Oh, I'll explain. Okay. So, did you guys see why a for any this thing is there? Now, I know the supremum would exist. I'm calling here the supremum as a. Okay. Now the point is the supremum. Now, if a is a preimage of some number n, some number k, I'll after k steps, it would go out. So that's why it's a contradiction. What? I'm using the nested interval principle. Oh, I should have stated that. Cantor's nested interval. Essentially, you take good amount of nested intervals. There will still be one point inside. Yeah, yes. So yeah, I assume that thing. This Cantor's theorem. This was Cantor's second proof to why reals are uncountable. This is very nice actually. This is very powerful. In the sense, forget about a bijection. I can't have a surjective function from A to the power set of A. Can't have a surjection. This essentially, if I'm working in the finite case, this would also give me another proof of why n is strictly less than 2 to the power n. Okay, sorry. So the proof is very simple. Um, I say suppose f is surjective. I essentially consider the set B such that um, B such that it's this collection of x such that x does not belong to f of x. Since it's a surjective function, I can consider the pre-image and then I'll arrive at a contradiction. Can you guys see why the contradiction is working? Take it. Okay, cool. Then we have diagonalization thingy. I cannot pronounce that. So that's why. Um, so how did Cantor prove that reals are uncountable? He considered power set. Power set of what? Huh? No, actually, that is too powerful. He worked with just 0 and 1. Binary, like just 0 and 1. And then what he did was, I have any like x1, x2 up to thingy. What he did was 0 point that, which is a real number. Cool. Okay. Take care. This would be an injection. Huh? Sorry. It won't be a surjection. It would be an injection. And this will be a small subset of the real numbers. And if the small subset itself is your uncountable, then the whole set will be uncountable. That follows. That's fine, right? Huh. And then he just said that this thing is uncountable. The set T, which is the binary, not the binary, but like just x1 up to the with xi being 0, 1. So he just mapped. Yeah. So oh, actually, never mind. Why did I do this? Never mind. I was so sorry. Huh. That was, okay, okay. The diagonalization thingy is different. My bad. Okay. So essentially, say you can list the numbers I said in T in a, like, you can list them. That is, they're countable. So suppose they're countable, then I'll just write them. S1 is your x1, S2 is your this, and so on. What I'll do is I'll create a new number S, which will be the diagonal, hence the name diagonal, elements. And this new number will be different than every other number appearing in this, which is, and the new number S also belongs to T. So we are arriving at a contradiction. I cannot list down T. So yes. And then I know that there's an injection. So I know reals are uncountable. Great. Everybody followed me, more or less. Yes, we're done. We're done with the boring stuff. Yay. Oh, fuck. Calkin Wilf tree. Do you guys know about Calkin Wilf tree? No? I see. It's nice. You guys will actually like this tree. I'll give you guys thoda sa time to discover the properties on your own. You guys will make conjectures. We'll see if your conjectures are true. Okay? Aditi, are you getting bored? Do you want a math problem to solve? Oh, okay. Hmm. So, how's the Calkin-Will tree defined? Well, at every point p comma, at every rational, like at every node p comma q, p by q, I'll essentially go to p by p plus q. This is me too. Turn off the AC, please. Can you turn off the AC? Yeah. Acha, can you sit that side AC? Oh, no, no, it's okay. यहाँ पे आ जाओ. My handwriting in board becomes really bad. Okay. Let me know if any one of you starts feeling suffocating. ठीक है. Cool, 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 cool. So I have P by Q. I'll go to the rational number P by P plus Q and P plus Q by Q. Oh, P comma Q GCD1. Cool. Everybody is fine with this? Okay. I'm starting with one by one. So can anyone say what the left node would be and what the right node would be? Cool. 3 by 1. Okay. Any conjectures? Conjectures. Do you want me to go to another level? Go on. Oh, yes, that's such a nice conjecture. That's true. Yes. Yes. Every rational number will appear once. That's actually very true. We can actually go and prove this right now. No, every rational appears. How about we say every rational number appears at most one? That is more easy to prove. Anybody sees y at most once? Yes. GCD will always be 1. So, and negative numbers can never be produced. So, yes, at most once. Any other basic conjectures? Basic conjectures. Hmm? Go on. Just say. Don't even raise your hand. Just say. Not really. This is actually related to Cernbrooked, which is sort of. I did actually research about it. There's not much relations to it. My goodness, I'll make the most dumbest conjecture then. Yes, yes. Oh my God. Yes, thank you. Yes. No, like product is nahi, but of each row. Product of each row is 1. It's okay. Just make conjectures. How about this one? I'll take the leftist one, and the leftist rational number will always be of the form 1 by n. See, make more conjectures. What about this? N. Maximum of p by q will be. That is true. Because the largest number is this one, and it's bounded above by. Okay, cool. More basic. Let's go with more basic stuffs. How many numbers are there in this row? Level. I'll go with level. Yes, power of 2. Cool. Nice. How about are they race? Go on. Yes. They are reciprocal of each other. Yes. Cool. Any more conjectures? If anybody is getting bored, because the GCD is always preserved. Because um GCD of P plus Q by Q is GCD of P comma Q. And I have assumed that 1 comma 1 GCD 1. Oh, okay. I'm saying that GCD is always 1. Yeah, you can actually go back. Oh, fine. I'll actually think we'll go there. Okay, so how about this? Whenever I have this number, say m comma n, this number I can go back. Okay. First, can you guys see? Yes, exactly. So see, first case is if I have this number m comma n, you check if it's greater than 1 or it's less than 1. So if it's greater than 1, I'll take the number. Give me a rational number now. Uh, 3 by 5. 3 by 5 is what? Greater than 1 or less than 1? Less than 1? So where do you think it would be? Here or here? I'm I'm right now I'm going conjecture wise. Uh, so yeah, yeah, it would be in the on the left. So it would be 3 by 2, correct? Where would it be? Yes. So it would be 1 by 2, which would be 1 by 1. So I am getting a unique part. It's a unique part. Keep that in mind. So if I have this as GCD1, this has to be GCD1. Similarly, this and this. Yes. Yeah. Induction. I did not actually, I was like, this is your algorithm. If it's less than 1, you do this. If it's more than 1, you do this. It's a unique thingy. Done. Um, huh, very basic claim, but if, oh, notations. Whenever we are dealing with graph thingy, parent, left child, right child, binary. So there can't be 3 childs. It is a child. Okay. So I have the parent x, then my left child would be x by x plus 1, and the right child would be x plus 1. I won't prove it. I mean, I'll let you guys be actually clear with the definition. X, then the right child would be x plus 1, and the left child would be x by x plus 1. Can you guys see why? Essentially, cool. Everybody fine with it? Nice, let's go. Smart kids. Uh, this is how my tree looks like. Very aesthetic. 1 by 1, 1 by 2, 2 by 1, 1 by 3, 3 by. Oh, so my main aim is to prove that rationals are countable. So what he said, Bhairav, if rationals are, if all the rationals appear here, then I'm done. Then I can simply give you the indexing key, just go this way. So F1, F2, F3, F4, F5. Cool. Let's go. Nice. I have this proposition, my conjecture. I'm going to prove it afterwards, thoda sa, because I want to prove other conjectures first. But yeah. So we already proved this, but all the fractions in the tree are, why I call this infinite Q tree because back then I did not know the name of the tree, so I called it infinite Q tree. Yeah. Are you guys like very serious? Why do you guys not laugh at it? This is okay. So if P by Q is reduced, then so is P by P plus Q and P plus Q by Q. Can you guys see why? We just talked about it right now. Cool. So if I have, so I then use induction over the rows. So if my kth row is all reduced, then by induction, and I showed this, then by induction, the k plus 1 at row would also be reduced. Cool. The left child of any vertex is always strictly less than 1. And the right child is always greater than 1. Yes. This is example. We don't really care about it. Every vertex is the product of the child. That is correct. Simple algebraic multiplication. Relations with the Euclidean algorithm. You didn't miss anything. Do you want me to go through it? Okay. Relations with the Euclidean algorithm. How many people know Euclidean algorithm? How many people know that it works? Like why it works? It's actually connected. Makes sense. Nice. Okay. So yeah, I have now defined. Nice. You guys are discovering it on your own. You guys should apply to promise. No. Okay, so this algorithm, which I call the cool sequence algorithm, I don't actually, it doesn't have a name, will give me the unique path from p by q to 1 by 1. And if I can, so if I can give a path for any rational number, that is essentially saying that, okay, I know, so this rational number should be there in the tree. That would prove that uh, rationals are countable. Yes, that cool. So what is my um so what is my cool sequence algorithm? I already talked about it because you guys said it. That huh. So the cool sequence. Oh no, I'll go till 5 because these people ask me to start at 3:45. Fine. Yes. So A by B. I need to see the pre-image of A by B. So what I'm saying is, if A by B is yeah if yeah if B is greater than A, then this would map to A by B minus A. That is why from 3 by 5 we were going to 3 by 2. Cool. And then if A is greater than B, then just go to A minus B by B. Do you guys see why? It's not even an algorithm. It is what it is. Like, do you see why this is happening? Yes. Aditya, do you want a math problem? Have you done what's the oh, okay, yeah. This is fine. Pakka. Okay. So here we did the backtracking. I had 13 by 47. So this is my A, this is my B. Clearly B is greater than A. So my backtracking would be 13 by 34. Go on, 13 by 21, 13 by 8, 5 by 8, 5 by 3, 2 by 3, 2 by 1, and 1 by 1. So I have this unique path. Can do it, can do it for any m by n, m comma n GCD1. So yeah, we proved rationals are countable. Lectures over. No, it's not. Uh, yeah, this was my path of the uniqueness. We've showed why the number of elements in each level slash row is 2 to the power n minus 1. Can you guys see why? Because we are starting with 1. It's Now, the ith node from the left is the reciprocal of the ith node from the right. Induction, basically. Do you guys want to see why? Like, do you guys actually want to rigorously prove it? No, makes sense. Induction paves the way. If something is done by induction, do not do it. Okay, product of all elements in the row is 1. Because we know it's reciprocal. So, nice, good. First node is 1 by n, last node is n by 1. So sum of the elements, it's a bit non-trivial. I'll ask you guys to prove it. For any nth row, the sum of the elements is 3 into 2 to the power n minus 2 plus 1 by 2. Try it. Please try it. Please, 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 please. Sum of all the elements, sum of all the nodes. Induction. Sorry, my bad. Minus. Induction works. If you know, if you know why induction works, then yeah. I'll think I'll show why it happens by induction. Suppose it is true for the kth row, I'll show it's also true for the k plus 1th row. Now I know the reciprocals exist. Okay? So I take any number a by b. I know in the kth row, a by b is there. B by a would also be there because reciprocals exist. And so a by a plus b, a plus b by b by a plus b, and a plus b by a. The childs of a by b and b by a, they exist. Add them up, you get 3 plus a by b plus b by a. Sum it up, because you're taking 4 numbers, you'll get 3 into 2 to the power k minus 2 plus 3 into k. I'm tired. 3 into 2 to the power k minus 2 minus 1 by 2. Induction works. Cheho. Let's go. Now, I, as we said, Euclidean algorithm is very closely related to this. I'll give you guys some few minutes to discover why. Why? Like, huh? It is something to do with continued fraction. I'm not actually involving continued fraction right now, actually. But since Euclidean algorithm and continued fractions are like just same, I want you guys to think about why it is traveling up the graph. Yes. Hmm. Yes. Correct. So when should I write the Euclidean algorithm thingy for 13 and 47? Thank you. Thank you. Thank you. But I'll start with the basic. When I write 47 here and 13 here, no, actually I'm writing it. Uh, I have 47 here. Like the main question is why am I getting 3L? Because it's 3 into 13. 8? Yes. 8. So the 3 is important here and there because um this sign, the sign when I say L and R, it changes when it gets less than the number, right? So that's why my sign changes. So that's why it's closely related to Euclidean algorithm. And when you convert it into the continued fractions, the indices in the continued fraction, that is essentially the indices of the number of lefts and the number of rights. And yeah. Now, my main aim right now is uh, there is this recursive formula of this. Recursive formula of which, okay. So if I have n here, I want to get the formula of this node. I want to, okay, so if I have fn is this node, I want to figure out what is fn plus 1 recursively. Now what we have is, this is n plus 1. My numbering is like this way now. My numbering is this way. G is F, okay, whatever. Huh. So see, I know the brute force way, which is go up, come down, magic. Should work. Like I know how to do it. It's just some bashy way. But I don't really want to do it. I want to figure out a recursive way. And this recursive formula is really, really, really good. This. Which is fn plus 1 is 1 by fn ceiling function. Ceiling floor function plus 1 minus the fractional part. So the main goal now is to prove this formula. Okay? Why am I doing this? Uh, because if you go to the Calkin Wilf tree ka Wikipedia page, this formula is there and there's no proof of it, which is really sad. It's very sad. It was very sad for me to figure it out. So it's okay. I'll make you guys learn, like, see the proof so that you guys can figure it out yourself. Wikipedia sucks. Chalo. Huh. It's connected with Euclidean algorithm. Go through it once. If you guys have any doubts, ask me. Any questions? No questions? Can I just... Oh, hold on. Oh, yes. Yeah. Some formulas. Um, if I have a fraction, not a fraction. Uh, if I have a number a by b, can you figure out which row it belongs to? Huh? Huh, it's 2 log, like log 2n, I think. Huh, that is... Would you like to explain why? Okay, or maybe... Actually, never mind. Uh, no, never mind, actually. Just- Sorry. Wait, it's related to this one? Is it? I figured out the end system. I don't think so. It's closely related, but like most of the problems, I don't know. This is very this is very normal number. Is the point. So, huh? It's very normalish number. Don't quote me somewhere, but like yeah, it's common to see it. So do you guys see how to figure out the row and the position it would be? Cool. This thing, the main thing. Think about it. How would you how would you do this? Like if you're given this in a contest, what would your first instinct be? Yeah, that's what we're going to do. But I think my first instinct when I see this in a contest, I hate fractional terms. This is very bad. I do not like this. It's very hard to handle this term. So do you guys know that fractional part of n is essentially n minus... So I'll first remove this term and put fn minus the fractional part of this, of fn, just for simplicity, because I cannot handle fractional part. So that's what I did. But and I think in general also, like when you solve IOQ and PRO problems, it's been like, I don't know, 3 years. I think my first instinct is definitely removing the fractional part. That's what I did. Do you guys see why this is true? Yes? Let's go. Now, no, okay. Now, um, there's some base, like some, like, okay, there's two case. Okay. First case is, I have this P by Q, and this is my Fn, and I want to figure out Fn plus 1. This is sort of relatively easy to count, to figure out compared to uh, this is my P by Q, this is my N by M, and I want to figure out f of k and then f of k plus 1. Ow. This thing is relatively. Okay. Back to this. If if I want to compute f of n plus 1 using f of n, I just basically have to do one step. Go up, p by q, figure it out. Boring. I don't give a I should control over my question. And then if I have f of n here, this is significantly harder. This is my so this f of n is my left child of something, and this f of n plus 1 is right child of something. How do I figure that thing? Like, I need a recursive formula, which totally only depends of f of n. So that is hard. So my first case is obviously, because I'm very coward, I'll deal with the easier case first. Sorry. Which is this case, which I can deal with it. One page proof. No, two page. One page. Huh. For any fractions, a fraction fn plus 1, where fn plus 1 is the left child, left. Oh, left, right. Um, is the left child, we can say that fn plus 1 is this. I can prove it. Anybody wants to figure out how to prove it? No. Yeah, that's why. That's why. Like, my point is, oh, you have a question. Previous died. You know what? We'll figure it out together. You know this thing, right? Uh, oh, you don't know this one. Oh, okay. So we use that thing there. You have proved this once. Oh, this thing is called the fractional part. Okay. If you have the number 1.01, oh, that is wrong. Okay. Yeah, we have to prove this. So let's prove it. Okay, cool. Since I know, okay, let me write this. This is my f of n. This is my fn plus 1. I know what fn, f. So what I'll do is, say f of, see, so we know f of n. F of n would be x plus 1. We actually, remember we figured it out. If the parent is x, the right node would be x plus 1 and the left node would be x by x plus 1. So if this is x by x plus 1, oh sorry, this is x plus 1, this is x, then this is basically x by x plus 1. I know what f of n is. So I can figure what f of n plus 1 is. It's just manipulation. This is how you end the proof. You don't figure it out. You just say it's just manipulation and then end it. Is there something wrong though? This side. Fn is the right child. So I'm going this side, right? Fn is, oh, I forgot to tell you guys this. My bad. Oh, my bad. My bad. Sorry, my bad. That's this formula, which I did not tell you guys. So I am converting the whole thing, like flipping it up. Okay. Okay, you know what? Uh, ठीक है. I have this formula, which, trust me, it's just manipulation, which, trust me, anyone can do it. Huh? See, the point is, I did a LaTeX error there. Everything here should be on top. Everything here should be on top. And I did that error. But what I'm basically trying to say is, this is my G. Okay? And I define G to be this. And now so I forgot to define what F is. F is this. F is not. No, wait. Trust me. I'm actually making sense. Listen. G is this. F is this. Which no, that isn't LaTeX. My bad. But what F does is simply switches it. 1, 2, 3. Yeah. Yeah, like yes. Yes. No, no. Oh, hold on. No. Can we okay, let's do one thing. Let's figure out together. F and G they should be ulta. Oh, okay. So the whole problem with this was I'm going this way, but but the recursive formula in Wikipedia went this way. And I'm very yeah, I didn't want to change my F. Sorry, G. So I ended up going this way. Okay, how about this? You stuck to this thing with me. This one is still this way. But, 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 okay, how about this? No, we'll figure this out and then I'll let you guys go. I'm so sorry. Okay. Okay. Yes. Let's figure it out with by our own. What is f of 1? No, what is f of 0? Oh, f of 1 is 1. Sorry. My bad. 1 by 1. What is f of 2? Huh? F of 2. Just अरे put करना formula में put कर. My God. उसके बाद what is f of 3? Yes. Yes, we are going left to right. I told the same thing to you guys. My God. You, my bad. Yes, my bad. But okay, everything is fine right now. We're going left to right. And that, huh? No, we are. Trust me, we are. I don't care. I don't think so. They'll post a recording with me cursing so much.